Why does this universe exist? Why many people will look and hypothesize about the existence of all things to the Big Bang Theory. It's still only a hypothesis we can use as a basis to be able to say with certainty if we're to split being of our feet. The Earth exists is the way all celestial bodies exist, is the way the whole universe exists. Everything is bound by a force, which is not even a force. And that is the basic foundational concept for the existence of all things to maintain all structures that ensure the relationship between matter and the universe. Gravity. In exploring the universe, one of the most surprising things is perhaps in those dust clouds. They could light and mass so many planets which are just huge gas clouds could be so heavy. It's just gas. But then when more and more gas is added to those spheres, it becomes heavier exponentially. A miracle has happened. A star is born. Why is this so? Why can these gas clouds be so heavy? Why do stars form from these clouds? It is all answered by a foundational concept of the whole universe, gravity. And everything began with a genius who looked at the sky and wondered what. When it comes to gravity, we often immediately think of the story of the falling apple that helped genius Isaac Newton to find the first laws of motion. You are standing on a ship as it moves forward. You will feel an invisible force as if someone is pushing you backward, making you fall backwards. Conversely, if the ship breaks suddenly, you will feel as if someone is pushing you forward. These are all motions based on the laws Newton thought of in 1686 in his work Principia Mathematicalis. Newton's laws have been the backbone for almost all physics theories we are studying today. However, this was not the only masterpiece this genius ever came up with. In 1666, when he was only 23 years old and looked at research on how matter behaves in this world by previous geniuses like Galileo Galilei and Robert Hooke, and said he understood what gravity is. According to Newton, gravity is the attractive force between 2 points of matter, or point masses that has a vector along the line connecting the 2 point masses. Despite much debate over who first conceived this notion, all scientists since then have acknowledged Newton's gravitational equation as the standard, which contributed greatly to the development of physics. However, many scholars are even more profoundly. Galileo himself also observed the existence of gravity and described it in his own words. Yet no one understood what gravity was and where it came from. This was only clarified nearly 200 years after Newton announced his masterpiece. Perhaps until now everyone knows the face of the whimsical man with a formula simpler than a times table. Albert Einstein. Born a special child with more functional brain than needed, he quickly became one of the pioneering scientists in the world in theoretical physics, and became the second most influential person globally. Looking at the laws of his idol and his gravitational equation, Einstein realized there were deficiencies that needed to be supplemented. To Einstein, knowing about gravity was one thing, understanding and applying it was another. So during the years 1907 to 1915, Einstein racked his brains thinking about this metaphysical concept and finally published the theory that caused the most breaks-up that termed the theory of relativity. Einstein's theory of relativity was immediately rejected by many scientists and considered a joke. However, when those theories were verified against the numbers, there was no mistake. And when no one could prove Einstein wrong, he was the one in the right. And his theory of relativity only supplemented Newton enough for not eliminating his work at all. So it was that same theory of relativity that was so important. When studying the theory of relativity, Einstein realized that the mass of matter was closely related to energy. This relationship was literally manifested through burning coal to create fire, but also related to the motion of heavy objects. An object placed high will have higher potential energy than a heavy object placed on the ground. The heavier the object at high elevation, the greater the potential energy. A brick placed on top of a cabinet when falling down could shatter the floor. So what about the moon? It's so high up there. So when it falls down, what would be the impact? These seemingly absurd questions lead Einstein to understand the nature of motion and the existence of space-time. All this time we have always thought of the Earth as a solid lump with great gravity on us. That means if we stand high, we will have potential energy. When we fall, we will fall to the ground. But when we think bigger, put ourselves in a very high and distant position, overlooking a person standing at tremendous height with the Earth far below, everything will be different. In this universe, nothing stands still. Everything is moving. The sun is flying through space. The Earth is orbiting around the sun, and we are standing on Earth. So using the Earth as a frame of reference would be no different from sitting in a car and thinking we are standing still. We and the car are standing still, and the world will move toward us. But if we stand outside the car, it is the one that moves. So in that distant perspective, is the person standing high jumping into the Earth? Or is the Earth falling towards them? The difference in perspective raises a question about the correlation of all things, the reason why everything moves according to the force vectors we have drawn. And if we look deeper, we will realize there are no straight lines that actually exist. Even the straightest roads are curved on the surface of the spherical Earth, the spherical universe alike. Nothing is straight, nothing is fixed. Everything is relative, even time. This universe does not have a common clock. 1 hour on Earth is not 1 hour on Mars. Each point in infinite space will have its own kind of time. Time is also relative because it is only a part in the infinite sea called space-time. And what makes an object at higher elevation have greater potential energy will be the very basis for the existence of gravity. Gravity, in fact, is not a force. It is the result of the interaction of matter and space-time. The heavier the matter, the greater its interaction in space-time, resulting in greater gravity. It is why the sun lies such enormous weight, because it is a supermassive lump. That is why we stand on Earth instead of floating around. And as the super-dense and super-heavy Earth creates a super-strong gravity that we cannot easily escape. Gravity is the result. Even a tiniest bit of matter has gravity around it, though it is extremely small. This means with its tiny gravity it can still attract other matter. And that is exactly what happened out there. When the universe was born, matter was shot everywhere and space-time expanded at tremendous speed and temperature. However, as everything began to cool down, space-time expanded slower. Matter could start condensing under the influence of gravity. Then over time, for millions to tens of millions of years, tiny hydrogen cloud suddenly became a huge hydrogen lump with mass up to hundreds of million tons. The fatter it is, the more it attracts surrounding matter. That fluffy cloud, which seems as light as feather, in fact is heavier than Earth. It continually attracts and accumulates matter around it. The bigger it gets, the stronger it attracts. The stronger it attracts, the bigger it grows. And finally, when it has attracted enough matter, it creates gravity so strong that it forces the hydrogen molecules to come closer together, creating conditions for electron exchange and turning into a completely new substance. This is nuclear fusion. Initially, gravity was not strong enough to force the molecules to come close enough. They were just a pile of gas floating around one another. 2 hydrogen molecules were forced close enough to form deuterium. 3 hydrogen molecules were forced together into tritium. And then this process continued, forcing deuterium close enough to tritium, and they had to attract each other when giving birth to an electron and turning into a completely new substance, helium. The process of hydrogen synthesizing into helium did not just give birth to new substances, but also released energy around it. The released energy can be identified in various forms such as light, heat, and electromagnetic waves. It does not stop there. This process also created a chain reaction forcing hydrogen to continuously turn into helium and release energy. From there, in the core of the gas lump that was suddenly light with thrust pushing out against the gravity forcing, causing the whole gas lump to flare up. This is exactly how a star is formed from small gas particles over time, accumulating into a huge nuclear reactor, labeling activating the nuclear fusion process like a nuclear bomb emitting light, heat. However, the above advantage only comes to gas lumps large enough. As lumps not big or fit enough to generate sufficient gravity will only be gigantic, gaseous planets. But why is this so? Why are some gas clouds only gaseous planets while others become stars? The main reason lies in the amount of gas it is around it at the beginning of the absorption process. If around the initial gas lump there is only a small amount of gas, it will not be able to absorb enough gas to become a star. But if around that gas lump there is enough huge amount of gas, it will have enough material to accumulate into a nuclear reactor in outer space. And where there are such huge gas masses like that, the answer will make many people exclaim. It comes from the masterpieces of creation, the galaxy dust clouds. Those nebulas. They'll provide enough material for a star to be born, and if those clouds are big enough, the accumulated gas will be even more. The stars thus formed will also have differences in shape, brightness and range. Larger clouds will surely have the conditions to create larger stars compared to smaller clouds. The larger stars are named giants. Even larger ones are supergiants. So how about our Sun? It is just an average star in the leaf stars. When it was formed, it was nurtured long enough and has not reached its final days yet. So, what are the final days of a star? Can stars die? It sounds sad, but the truth is stars also have days they must pass away. It's just that those days could be hundreds of millions to billions of years away. Why do stars die? A star's existence completely relies on the balance between gravity forcing the ongoing nuclear fusion reaction and the force emanating from the core where the reaction takes place. The force radiating from the nuclear fusion helps the star shine and continue its life, while the star's gravity will force the nuclear fusion reaction to continue. So as long as they are balanced, the star will live. So what will disrupt this process? The answer is quite easy to guess. If the nuclear fusion is sustained by hydrogen being fused into helium, what happens when the star burns up all the hydrogen in its body? For average-sized stars, this is when it starts to thin in nuclear fusion process and expands into a huge red giant. When it expands enough, its gas mass will be released into the galaxy in the form of a nebula, a huge cloud surrounding a bright core where it is still very bright, but will gradually cool down and fade because the nuclear fusion action has completely ended. This is a white dwarf, extremely compact and bright but no longer generating energy. However, this is for average-sized stars. What about a supermassive star like a supergiant? Everything goes according to the same progression. It still expands and migrates into a great supergiant, but then things start to differ. Although the star has expanded and started losing energy due to its still enormous total mass, gravity is still too great, so the nuclear fusion is forced to continue. From helium, the star will force it to synthesize into the next substance, carbon. Up to here, can the star convince the reaction to continue? The answer is yes. The nuclear fusion reaction radiates energy to balance gravity so the star can exist. But that is when we synthesize hydrogen into helium. When synthesizing helium into carbon, the radiated force is weaker than the previous synthesis process, causing the gravitational balance to completely disappear. And now the star continues to succumb to the enormous gravity of itself. Then from carbon, the star continues to synthesize into neon, from neon into oxygen, from oxygen it forces the creation of silicon. And when it reaches silicon, something bad will happen. Silicon can only synthesize into iron, but for iron to continue synthesizing into the next substance, it not only lacks the energy to fight against gravity, but also requires even more energy just to maintain the synthesis process. So when silicon is synthesized into iron, the star has completely lost in the chess game of balance between gravity and nuclear fusion. The star self-destructs into the most magnificent explosion in the universe called a supernova. What happens after the supernova explosion will depend on the initial mass of the star causing the explosion. If the star has just enough mass, the explosion will give birth to a neutron star, an extremely compact and super bright image lamp spinning extremely fast, emitting huge magnetic fields. But if the star is supermassive and gigantic, what then? An ultra-huge, massive, giant star, after synthesizing iron self-destructing into a supernova. The remnants will be beyond our imagination. However, it is still within Einstein's imagination. According to Einstein, when a supermassive star explodes into a supernova, what is left will still have a supergravity, and gravity stronger than anything we could ever imagine. stronger than any fundamental star and because light cannot escape the gravity of the supercompact mass, we cannot see the supercompact object. Hence, the conception of a black hole was born. This would be the place where light cannot escape, carry on as a massive weight in an extremely compact space, causing its gravity to be beyond imagination. This lump is so extremely dense that we do not know what impact it will have on spacetime. Will it be able to break spacetime, or will it just warp spacetime to such extent that it becomes incomprehensible what it even looks like anymore? However, which way all the information above, the whole story just told is only a small piece in its super genius, super brain. He gave everyone the theory of relativity, and he also imagined something called a black hole. Everything is still hypothesis and imagination, yet it is so realistic that everything we see in the sky aligns with that hypothesis. Only that hearing is not equal to seeing. So when we cannot see black holes, how can we believe they exist? That would be a question we need time to answer. In summary, this was the origin story of gravity, the origin of black holes, and the life cycle of a star. I hope you enjoyed the content we brought up for you. And if you like this video, please press like, subscribe to us, and click the notification bell so you won't miss any future videos. Thank you all for listening and seeing next time. Here is a sentence in English. Gravity is the fundamental force that shapes our universe, from tiny atoms to massive stars and galaxies.